This is video 5 of a 7-video series on hypothesis testing, two proportions. Here's an example of a problem that compares two proportions. Suppose we were asserting that Republicans are more likely to own a dog than Democrats. The reason why this is a claim about two proportions is because what it's really saying is this. There's a certain proportion of Republicans who own a dog, and there's a certain proportion of Democrats who own a dog. And this claim is asserting that the first proportion is greater than the second proportion. So now that we have this proportion about two claims, let's test it with a 10% significance. What does it mean, 10% significance? Well, to understand that, we have to talk about something called a type 1 error, also known as a false positive. Suppose we conduct a study, and in our sample, there's way more Republicans who are dog owners than Democrats. Now, is that proof of the claim that we're making here? It may be, but isn't it also possible that the two groups are equal in terms of dog ownership, but the particular sample that we choose just so happens to have a higher proportion of Republicans to a degree that is statistically significant? Then what if, in that circumstance, we then accepted the claim as true based on the one sample that we chose, which just so happened to be skewed by chance? That would be a false positive. Now, to say that we're testing a claim with a 10% significance means that if the probability of a false positive is anywhere up to but not exceeding 10%, then we're going to consider that low enough to accept the claim. That's what we mean when we say we're testing with a significance of 10%. So here's our sample data. 500 people were surveyed. 200 of them were Republicans, of which 98 had a dog. 300 of them were Democrats, of which 114 had a dog. Notice the proportion of Republicans from our survey that have a dog is 49%, while it's only 43% of the sample. 43% of Democrats in the sample owned a dog. So it's worth noting now, and it'll be important later in this problem, that there's a 6% gap between these groups. Now, the question we have to answer is that 6% gap statistically significant enough to accept the claim that Republicans are more likely to own a dog than Democrats? Well, as usual, we'll start our 5-step hypothesis testing by noting that step 1 and 2 have already been done for us. And if you're a student in a statistics class, step 1 and 2 will almost always be done for you. The claim and significance will be stated in the problem. The random sample will already have been gathered and the results printed in the problem. And we're starting with step 3, which is assuming a mindset of equality. So in this case, we're going to assume that the population proportions are equal. And if we're going to assume that, then we need to know the percentage of overall people from the two major political parties who own a dog. Because if we're assuming that the population proportions are equal, then we're going to look at this sample as just an anomaly, and we're more interested in the total dog ownership among the two major parties. So what I'm going to compute here is the overall sample proportion. Notice I have the 500 people surveyed, and it's not stated in the problem, but if you add it up, out of those 500 people, there were 227 dog owners. And that works out to an overall percentage of 45.4% dog ownership. And why are we assuming the population proportions are equal when it seems like we're trying to prove the exact opposite? Because if we assume they're equal, and we can show that this sample data, this 6% gap, is highly unlikely to have happened by chance in a world where the population proportions are equal, then we can cast some doubt on that assumption, known as the null hypothesis, and turn our favor towards the alternative hypothesis, that which we are trying to show. So in the assumption that the two populations are equal, let's look at a sampling distribution of what the Republican proportion minus the Democrat proportion would look like. Now, when I put this here, I am not referring to the 49% and the 43% of our particular sample. Instead, I'm doing a sampling distribution which poses the question, what would the Republican proportion minus the Democrat proportion look like if we were to repeat this 500-person survey over and over and over repeatedly? Well, what would happen in a world where there was no bias in terms of dog ownership for one party or the other? Well, if that were really true, then sometimes the Republican proportion would be higher, and this subtraction would be a positive number. And sometimes the Democratic proportion would be higher, in which case this subtraction would be a negative number. But overall, the difference of the sample proportions for each party would tend to cluster around 0, if in fact the population proportions were equal. The question we have to ask is this 6% gap close to 0 so that it could have happened by chance, or is it far enough away from 0 where it's unlikely to have happened by chance? And that's what we'll address here by computing the probability that the samples could vary this much. So we have a claim regarding two proportions, and this sampling distribution above has a standard error that's given by this formula. It should be noted that the p-hat in this formula is the p-hat total above the 45.4%. So we'll compute the standard error for our sampling distribution, and then we'll compute our so-called test statistic, which is essentially the number of standard errors our particular sample is away from 0. And because we're doing proportions, we'll use the normal distribution to find the probability that there could be a 6% gap between the groups in a world where there was no population bias in either direction. So plugging in all the numbers gives me a standard error of about 4.5%. And so the question now is, that 6% gap that we noticed in our particular sample, how many standard errors is that? Well, we would divide to find that out, and it turns out to be 1.32 standard errors. So what we'll do now is compute the probability of there being 1.32 standard errors in our sample, which leads us to 9.3%. So what does this mean? It means that if the null hypothesis were correct, that there was no difference between the two political parties in terms of dog ownership, that the probability of us getting a 6% gap in our samples is only 9%. And from that, we can draw our conclusion by comparing that to the significance. Our goal in this problem was to conduct a survey in which the probability of a false positive was less than 10%. And we've done that because we've shown that the probability of this being a false positive is 9.3%. And since 9.3% is less than 10%, there is, in fact, sufficient evidence to support the claim that Republicans are more likely to own a dog than Democrats. Here's another example. Suppose we wanted to show that men are more likely than women to buy a certain product. And we want to test this claim with a 5% significance, which again means we want to conduct a study in which the probability of a false positive is less than 5%, which will give us enough confidence to accept the claim. Here's our sample data. 140 people were surveyed. 90 of those were men, 45 of whom bought this product. 50 of those in the survey were women, 20 of whom bought this product. So you'll notice that for our particular sample, 50% of men bought the product, while only 40% of women bought the product. And of course, you'll note that there's a 10% gap between the groups, and the question we're addressing here is that 10% gap statistically significant? Well, you'll recall in the previous problem, there was a 6% gap, and we ended up deeming that statistically significant enough to accept the claim. So here's a question. If a 6% gap is significant, shouldn't a 10% gap be even more significant? Well, not necessarily. It depends on the circumstances and in particular the sample sizes. You'll notice in this particular problem, we have 140 people surveyed, which is a much smaller survey than our 500-person survey done in the previous problem. But let's proceed and see mathematically if this 10% gap is significant or not. So we're on step 3, which is really our first step in hypothesis testing because steps 1 and 2 have been done for us in the problem. So we're going to assume, contrary to what we're trying to show, that the population proportions are in fact equal, that men and women are equally likely to buy product X, whatever that is. And to do that, we need to consider the total survey. Now, these numbers are not stated in the problem, but if you look at the sample data and add it up, you'll notice there were 140 people surveyed overall, and 65 of those people bought product X. And under the assumption of equality, where we're not distinguishing between men and women, and simply looking at the total, we see that 46.4% of people buy product X. So now, why are we doing this? Well, the same reason we always do. If we can show that the sample data, that this 10% gap, based on this assumption of this null hypothesis, is highly unlikely to have happened by chance, then we have strong evidence to accept the claim that men are more likely to buy this product than women, which also known as the alternative hypothesis. So let's look at what a sampling distribution would look like for the men proportion minus the women proportion in terms of samples. Now again, in this case, I don't mean 50% minus 40% for our particular sample. The sampling distribution poses the question, what if we were to conduct this survey, this 90 men, 50 woman survey, over and over and over again, and look at what the men proportion minus the women proportion distribution was like. In other words, what if we were to consider this over the long haul? Well, if there's no difference in the populations, then sometimes the men proportion would be higher, in which case this difference would be a positive number. And in some cases, all things being equal, the women proportion would be higher, and then this subtraction would be a negative number. But overall, assuming the population proportions are equal, we can assume that this the distribution of this difference would hover around 0 most of the time. And that's what this sampling distribution represents. And so we have to then answer the question, is this 10% gap close to 0 and statistically insignificant, or is it far away from 0 and statistically significant enough to accept the alternative hypothesis that men are more likely to buy the product than women? Well, only the math will show. So now we're going to compute the probability of this 10% gap. Using the same formulas we saw in the previous problem, notice the p-hat again is the 46.4%, the overall percentage of people who buy the product. And what we find is that we have about an 8 or 9% standard error in this problem. Now, before I go on to any calculations, remember our gap between the groups here is 10%. And that's not much bigger than one standard error, you'll notice. And generally speaking, while I haven't finished this particular problem, in general, a difference of one standard error is not usually statistically significant, because a standard error, in some sense, is the error that we would expect between the men and women proportions if the population proportions were equal, which is what we're temporarily assuming. But to be more formal about the mathematics, if we divide our gap by our standard error, we'll find out that this 10% gap represents 1.137 standard errors. And calculating the probability of such a number of standard errors leads us to 12.8%. What does this mean? It means that if men and women were equally likely to buy product X, that this 10% gap has a 12.8% chance of having happened randomly. And now we can use that to look at our conclusion. Remember, we set out to find the probability of a false positive less than 5%. But because of our sample data, we've discovered that there's a 12.8% chance of a false positive, which is higher than we were willing to accept. And since 12.8 is higher than 5, we have to say, as big as a 10% gap may seem in sample data, that it is not statistically significant enough to support the claim that men are more likely to buy this product than women. And that completes lesson 5 of 7.